All right, where's the pointer? All right, thank you. Thank you for coming. So my research is about wildfire detection using geostationary satellites and machine learning. My supervisors are Arnon Karnieli from BGU and Boaz Nadler from the Weizmann Institute. Okay, so let's talk about extreme fire events. If we take the frequency of extreme fire events from 2003 to 2023, we can see that it increased by almost two-folds, like more than two-folds, which most of the events are, let's say, in the northern latitudes of around Siberia and North America. You can also see it because we have some other parts of the world. So that means that rapid fire detection can prevent huge scale disasters. As long as we detect the fires more faster, we can prevent the disasters. So we can use satellite imagery to detect fires in real time, and usually there are two types of satellites we can use for wildfire detections. So the first type is low Earth orbit satellites. They orbit the Earth at altitudes of around 400 to 700 kilometers. The spatial resolution is between 30 meters to 1,000 meters, depending on the sensor. They usually have multispectral sensors that can catch fire signals, and their temporal resolution at best are every 12 hours, and even in some cases up to 16 days for the same place on the Earth, which make them not suitable for real-time detection. On the other hand, we have geostationary satellites at an altitude of 36,000 kilometers with a spatial resolution of between 500 to 2,000 meters per pixel, which is much coarse. And they are also multispectral with bands that can detect fires. And the temporal resolution is, let's say, between every 5 to 15 minutes, which make them more suitable for real-time detection. Okay, so in addition, these satellites already have fire products. Here you can see an image of a fire from a low Earth orbit satellite. And here you can see fires in California from a geostationary satellite. You can see the difference in the spatial resolution. So for each type of these satellites, you can have fire products. What does it mean? That means that usually the agency that sent these satellites into space, they build some algorithm for fire detection. So usually for each pixel, you get a classification, whether it's a fire or not a fire. So here it will be in a resolution of 375 meters per pixel, and here you will have 2 kilometers per pixel. All right, so what is the challenge? We already have the satellites, we have the fire products. So let's talk about the challenges with wildfire detection. So here you can see in this column the 3.9 micron band, which is very suitable for detecting wildfires. And on the right, you can see the fire product of the geostationary satellite. Okay, so here you can see that at 227, you can see the fire in the 3.9 band, and on the fire product, you don't see anything. And the first time the fire product detects the fire in this red small pixel here, it's at 252. That means that we have 25 minutes delay between we can first see the fire using the 3.9 band when the fire product is actually detecting the fire itself. Okay, so it's a lot of latency in detection. The second problem is high false alarm rates. You can see all of these colorful pixels. These are pixels that were classified as fires by the fire product of the geostationary satellite, but they were not fires. It's a solar panel farm, as you can see here. So from recent paper in the work, so there are, let's say, 35% of the pixels classified by geostationary satellites are false alarms. So the product is not so reliable. So we had a few goals. The main goal is to develop a machine learning model for fire detection, which is more accurate than existing fire products and has much more low false alarm rates. Okay, so now we will talk about the framework of the machine learning. First of all, we have the input, the things that go inside the model. So we used the American GOES 1618 ABI geostationary satellite. It has 16 spectral bands, spatial resolution of 2 kilometers per pixel, and a temporal resolution of every 5 minutes. For every 5 minutes, you get this image of the whole US. And on the other hand, we have LEO fire detections, low Earth orbit fire detections in a high resolution from the VIRS instrument in a 375 meters in a temporal resolution of 12 hours. So basically, we took the fire pixels from the high resolution VIRS satellite, and we can fit them, the temporal match of them, to the GOES satellite and see where we had fire pixels, and so we can label the model for which pixels are actually fire. So this is our study area. As you can see, we have this area for evaluation, California and Oregon. We have this area for training and evaluation. And you can see the land cover types are really heterogeneous. And in addition, we use some of the training states also for evaluation in different years and time periods. So, of course, we won't have a bias in the data. So we collected data from years 22 to 23. The training area is about 2 million square kilometers. The evaluation area is 1.5 square kilometers. So it can be really general, and we can see we can transfer the model to large places. We have more than 300,000 VIRS fire detections. We have more than 4,000 GOES satellite images. All of this went into the model. The next step was feature extraction. It's actually to choose which parameters from this image we want to teach the model with. So let's say we have this GOES ABI grid. This is the grid with the pixel. And let's say this pixel was annotated as fire by VIRS. Okay, so first of all, we calculate the fire index for this pixel using the bands 3.9 and 11.2 micron. Basically, what you need to know from this is that values above 0 are likely a fire and values below 0 are not a fire. In addition, we treated this fire index as a band, so we took all the 16 spectral bands in addition to the fire index as input to the model for each pixel annotated as fire. And in addition, we took the contextual information of all the neighbors around the pixel that was labeled as fire. That means we took the mean of the neighbors, the median, the minimum, the maximum, and the standard deviation. So we have 17 bands or 17 matrices and 5 contextual and 5 statistics. So it's 85 features going inside the model. And in addition, we have the 17 values for the fire pixels. So it's 102 features for every pixel that we teach the machine learning model. Okay, so in total, we trained the model with 66,000 fire pixels and 1.4 million non-fire pixels that were randomly sampled from the images, and we make sure there aren't clouds in this non-fire pixels, and they were not containing any kind of fire or were not close by to near fires. Okay. Then the model goes through some kind of learning, and then we can make classifications and predictions to the new input data of our machine learning model. And we get an output, which is basically a binary classification if a given pixel is a fire or no fire. So let's see how it looks in when you put it in the for a test. So this is VIRS fire detections. As I said before, it has a much higher spatial resolution. So you can see many fire detections in the state of Texas. But if you can see here, some large fire events, here, and here, it was spotted also by the machine learning model. So the machine learning model can detect the large fire events. And if we zoom in, we can see the locations of the fire detections. We can also see, if we take another closer look, we can see that these red pixels here are true positive. That means that these are fires that the model predicted as fires, and they were actually fires. And it's validated by the VIRS fire detections. This is like the small green squares are VIRS fire detections. So you can see we have them. In addition, we have fires that the machine learning model did not detect. Right here on the right, these are in a blue color, and this is because these are small fires. You can see there is only like one VIRS fire pixel in each ghost pixel, so it's hard for the sensors to detect them. And also we have false alarms. This purple pixel over here was labeled as fire by the model, but actually it's not a fire. Probably it happened because of the proximity to the fire, and we assume that this pixel was heated and the model was confused. So the next thing we did is to evaluate our model to see how well the model performs on a large data set. So we took data from 2024, which was not the training years. We took it from a separate year. Then we took 3 months of data for each region. So we took 3 months of data from Georgia, Texas, and California, Oregon. And we used VIRS as a reference ground truth to see if our model detects the fire or not. And in addition, we compared our results to the GOES current fire product, which is available to the public. So let's see how well the model is actually performing when we test the model. So the first accuracy measure that we used is precision. What you need to do to know of precision is from all the fires the model predicted, how many were actual fires. Okay? So when the number is closer to 1, that means better performance. So on the blue we have the machine learning model, and on the green we have the ghost fire product, and we can see that in Georgia it's got the same score. In Texas and California, the machine learning model was performing much better. That means from all the fires it detects, much more of the fires are actual fires. Next was recall, so correctly identifying fires from all the actual fires in the dataset. So how well can my model detect fires comparing to VIRS? So as you can see, the machine learning model outperformed the GOES fire product in all of the states, performing much higher. And we have the F1 score, which is the harmonic mean of precision and recall. And we can see that the machine learning model is, let's say, much more superior to the current GOES fire product. Okay. So what about, so we have more lower false alarm, more accurate detection, but let's see, how about early detection? Can our model detect fires better than the GOES fire product in time when we talk about early fire detection? So we took 42 fire events in this area from all of these states. Between the years we took from 2021, 2024, and 2025. And for each of these fire events, there are documented fire events. Oz mentioned that it's really easy to collect data in the US. So you have a lot of documented fire events with their fire perimeter and their starting date. So it's really easy to collect the data. And so for each of these fire, we compared who detects the fire first. So you can see from, okay, so the blue color is when the machine learning model detected the fire first, and you can see the time difference between the early detection of the machine learning model and the GOES fire product. So you can see in many of the fires, I don't remember the exact number, I guess more than 20, and the machine learning model detects the fire earlier from the GOES fire product, up to 65 minutes difference. And on the other hand, only 4 fires were detected earlier by the GOES fire product. All the fires that are labeled as 0, it's when both of them detected the fire at the same time. In addition, you can see, for example, this fire, the Bobcat fire in Florida. For this fire, the machine learning model detected it in 20 minutes earlier than the GOES fire product. In addition, we have fires that only our machine learning model detected, and it detected it much more faster than VIRS, even faster than the high resolution, because it has a temporal resolution of 12 hours. And there were some fires that not the machine learning model and not the GOES fire product were even able to detect. These are much smaller fires that were not detected. Okay, so the machine learning model has superior early detection capabilities. Another test that we ran is to see which model has the higher probability for detecting a fire as a function of the fire size. So basically here we have the blue line as our machine learning model, the green line is the ghost fire product, here is the probability for a fire detection, and here's the number of Vir's fires detection inside the ghost fire pixel. If you remember from earlier, there were green squares. It's how many green squares are inside the ghost pixel. So you can see even for one Vir's pixels inside the ghost pixel, we get a much higher probability for a fire at the machine learning model. And of course, as the number goes up, it makes much more sense that both models will be able to detect the fire. And when we take 10 Vir's fire pixels inside the ghost pixel, we get almost 0.9 probability for a fire detection. Okay, so let's do a short summary. The machine learning model outperforms the current ghost fire product in terms of false alarm rates. It has much more higher precision in early detection time and in fire detection probability. You can use the model, you can scan this QR code, and you can download ghost image. You can, there is a GitHub repository. It's you put the image inside, and then it's you can predict if there was a fire or not. So it's a nice thing to play with. In the future, the model will be implemented to the MTG satellites. So the European NGC, Space Agency, sent the MTG satellites a few years ago. The data is available from 2024. And now we will also detect fires using the MTG over Israel, the Middle East, Europe, and yeah.
Oz. Thank you. It was very interesting. Good results. Did you do, I assume you used all the 16 bands of the satellites? Did you do any sensitivity analysis to see which bands are more informative? And from my experience, you should remove all the ones that are not informative, and it will increase your let's say probability even more. So I don't know if you did it, but I think if you do it, your results would even be better in this sense. I think you should try it. It would be a very good addition for I assume a paper which is going to be published. Both the sensitivity and the reduction of uninformative bands, it will improve your model.
Anyone else? Thank you, Asaf. The next talk will be done by, who is here? Seifu? Okay. Sorry for the misleading with the name. Okay, great.
Yeah, thank you very much, Arnon. My name is Seifu, and I am a PhD student of second year. We are working on remote sensing-based hybrid modeling for sediment sampling suitability in support of geochronology in Karakum and Kyzylkum sandy desert, which lies on Central Asia. This is a first trial of remote sensing application for geochronological purpose, and my supervisors are Dr. Leah, Shumris Maman, and Dan Bloomberg from the main campus. Hours. Yeah, I think we can start. Okay, thank you. So, climate change and desertification are the major challenges nowadays threatening ecosystem and biodiversity and human livelihood. And we saw drylands occupy most of up to 40% of the land surface. Understanding these deserts or dryland geomorphologies and geology is essential for reconstructing past climates and also to assess long-term environmental changes. Thanks to the advancement of technology, nowadays remote sensing provides various or different satellites images for remote deserts, and this greatly improves geomorphological studies and also geological studies in vast and inaccessible deserts. So the main motivation for this study was OSL dating techniques are used for reconstructing past climates. So OSL provides a robust technique for reconstructing sediment depositional chronologies when sediments was deposited. This sediment, these OSL techniques, however, it needs appropriate sediments from appropriate location, unless it will mislead the chronological timing of sediment depositional age. So usually field sampling relies on expert judgment on field. So this makes time consuming and also hindered by logistical limitation in the vast deserts. So without prior spatial modeling, researchers risk undersampling key geomorphological units and also oversampling but less representative sediments from the field, and this leads to be biased and unreliable OSL chronologies will be happened. Therefore, we developed spatial decision-making framework to optimize sediment sampling strategy for to obtain precise edge estimates. So the main objective will be to generate suitability maps that can guide pre-field sample site selection before field deployment. And secondly, we will assess feature importance and also sharply additive explanation values to understand each contributor values to final suitability sampling area findings. So where we apply in the vast desert of Karakum and Kyzylkum, which was found in Uzbekistan and Turkmenistan, and a little bit of on the Kazakhstan region. These deserts are believed to be created on the Neogen era of geological time, and according to Köppen classification system, these deserts are found in cold and dry mid-latitude regions. So for data predictions and also to use for models, we considered various sources based on data availability for the region. These variables came from environmental, climate, and geomorphological context. Its purpose was to identify quartz rich and undisturbed sediments for OSL luminescence integration. So we used various models. The first one is analytical HP model, which will be usually used as expert knowledge or based on literature reviews to determine the relative importance of each variable from each other and to weight and rank based on decision metrics. We attain the weights or importance of each input variables. The second one is entropy theory. We applied here entropy to counterbalance the HP is more subjective nature. So the entropy is based on the objectivity. It depends on the variability on the data sets. So we consider the entropy theories here also, and also we will integrate this HP and entropy theories to techniques for order preference, or known as TOPSIS. These TOPSIS rank sites based on their proximity or Euclidean distance from best or ideal positive to the worst ideal negative regions. And finally, we assess with the machine learning models. We chose two machine learning models, random forest and extreme gradient boosting, to predict the final suitability. So we use these four models based on the multi-criteria approach and the machine learning techniques. So in general outline, we use the data sources from various sensors of remote sensing, and also we attain from various sources the NDVI, the moisture index, wind speed, quartz precipitation slope, surface temperature, temporal stability, and road network. Finally, we used, based on the data nature, we use data processing and scale uniformity, because we have various scales based on the data nature, and we make to normalize each factor layers to be uniform for multi-criteria decisions. And finally, we assess the multicollinearity of each variable inputs, because it may lead to multicollinearity if they have high correlation to each other. And unfortunately, we didn't get high correlated variables, and we include all input layers for prediction and for multi-criteria uses. So we selected the techniques, the decision tools like HP and entropy, the machine learning models, and finally, to attain the final consensus results, we will combine the final maps to find the final optimal regions based on fusion techniques. And finally, the attained results or before prediction, we assess the future contributions, and each model output will be finally validated based on the ASC receiver operating characteristics. So based on the model results, we attain the weights. The HP will be subjective weights, and the entropy will be objective weights from data variability or diversification, and the random forest and extreme gradient will be used with internal modulator to before prediction. The models first rank the factors based on the nature of the predictor. So the sharply additive explanation, this sharp analysis is used to know which variable have any more contributor to the final output of the model. So when we see the sharp results, the positive values and the negative sharp results. So the positive values have modulated the prediction to high suitability, and the negative sharp values pulling down the prediction down to low suitability of our region. So we attain here quarters is more in the values of high quarters regions of high values of quarters are predicting the suitability to the higher, and in contrast we will see it in the high temperature values pulling down the prediction to negative sharp value results. We obtain unexpected results from here. The wind speeds are mostly hypothesized that to transport sand in arid regions, but basically here it's have a lower contribution to oil cell sampling because of it will be lower contribution for sediment composition. So these are the each values results, and finally we attain each model results based on the model types with HP and XG boost result, entropy and random forest. And we finally get from this model, we have a consensus result of fused suitability model from very high to very low to very high suitability regions. So the identified sites finally assessed based on the accessibility to the road networks. So finally, if you found the sediment sampling regions, you have to care about the accessibilities. We assess based on the access to paved roads, and we found some regions from available road network within a distance of 50 kilometers in the route. So we attain zone 2, 4, and 5 have a high suitability regions and hopefully accessible based on the road availability on these deserts. And then additionally we assessed based on desert classification, which will be dune type classification in the deserts. There are various dune types. So mostly in this Karakum and Kyzylkum region, we do have a vegetated sand, vegetated linear dunes, and also bedrock, solonchak, and taikir are also existing. So we assessed those predicted maps of in where it lies. So mostly in the vegetated linear dunes and the vegetated sand most occupy the high suitability regions, and the high regions across all values from low to very high. The solonchak, bedrock, and takir mostly shown in the very low regions, and it implies they have not. It implies it's not good to sample here because of its salty nature. So we assess this one. So after finalizing all the models, we have to check about the validities of predicted models. We tried to evaluate the model performance and also the multi-criteria models based on the known techniques, AOC-ROC, and we attained the fused suitability up to high prediction. On the HP topsies, we attained somehow lower OSC value of 0.84. We attained. In conclusion, considering those variables from environment, climate, and geomorphic control play a critical role in selecting reliable oil cell sampling sites. And finally, it will help us to reduce reworked sediments and improve chronological precisions, and also fusion of multi-sensor remote sensing from different sources and from different sensors with advanced techniques produce high suitability maps that can guide our field before our sampling before field, and integrating remote sensing with oil cell dating, and this framework boosts dating reliability and provides a strong foundation for reconstructing desert paleo-environmental research. And in the future, will could be sediment sampling in this region using sediment sampling tools. In the field, hopefully, we will sample from these identified regions. And thank you for listening. If you have any question. Suggestion, maybe. It's better.
Thank you very much for this presentation. Last and not least, this is the presentation of my group, and we analyzed the EnMap and EnMap derived Crusts spatial spectral indices. These two satellites are quite new. They are hyperspectral with a lot of bands, so there is lot of information that we can derive from these satellites. Okay, we are talking about biological salt crust, we call it biocrust, which are communities of microphytes and tiny organisms that locate the topsoil in drylands, especially in drylands. And although biocrusts are a few millimeters thick and colonize only the topsoil, they have a virtual ecology role in the ecology in the critical zone, including stabilizing the topsoil and prevent surface erosion, alter the water regime and influencing the infiltration, runoff and evapotranspiration, controlling nitrogen cycles and by impacting nitrogen and carbon fixation, changing the land surface temperature and the microclimate on a regional scale, and therefore for protecting and restoring the biocrust, considerable effort has been devoted for monitoring and mapping them, primarily using spectroscopy and remote sensing methods. Few examples for the biocrust. This is cyanobacteria from the Negev. Here we see the upper part of the dune, exposed soil, but all this area is covered by cyanobacteria biocrust. This is from Namibia. This field is covered by lichens. And another example is from China. All this area is covered by algae. Okay, so you see the vast spread of the biocrust and the vast cover areas of biocrust enable the use of satellite images. Let's talk about the pigments that contains this microorganism. The first one is the chlorophyll A, which represented here by the green curves. The second is the carotenoid, the orange. The phycobilin, it's the blue, and cytonemine, it's in the magenta color. So these are the four pigments that appear or exist in this microorganism. So the goal of the study is to use biocrust-related pigments and cellulose content for mapping the biocrust based on the hyperspectral spectrum sensor, as I mentioned before, the EnMap and the EnMap in different parts of the electromagnetic spectrum. So which parts we can use? First of all, is the near infrared. You see here the reflectance levels of dry soils in orange and in brown the wet soils, and the dry biocrust in cyan, and the green represent the wet biocrust. So you see that these differences, we will talk about it in a minute. Okay, the second is the near ultraviolet, and the blue, and the red, and the SWIR 2. Now, if we are collecting a lot of samples in the field, we are getting a bunch of reflectance curves, reflectance versus the wavelengths. When we are running wetting experiments, we get another set of curves. What we are doing with all this, we are running, first of all, the partial least square regression. This is a well-known procedure in order to distinguish between the different curves, or to distinguish between different parts of the electromagnetic spectrum. Before running the PLS square, or in part of this procedure, we are applying a pre-processing. A pre-processing is a mathematical manipulation, like smoothing, auto scale, weighting, and several more. And from this set of curves, we are getting this set of curves that you can see that there are different features that stands below and below the main curves. And one of the byproduct of this PLSR, partial square regression, is the variable importance of projection. This procedure is enabled to find the most important wavelengths that exist in the curves, and distinguish between different elements or different soil crust, the same between the wet and the dry, and some other elements like the pigment and the cellulose that I mentioned before. So the procedures talk about a threshold of 1, and when the value or the score of the VIP, the variable importance of projection, VIP, that means that it's important for the element that we are looking for. So what we found here, first of all, the near ultraviolet has a very high score, then the blue, the red, the near infrared, and the SWIR 2. Okay, so we are talking about two satellites, two new satellites, relatively new satellites, the EnMap, which is launched by ESA, the European Space Agency, with the spectral range between 420 to 2450 nanometer. That means between the blue and the SWIR 2, and the spatial resolution is 30 meters. The second is the EMIT, launched a few years later by NASA, with the spectral range between 380 to 2500 nanometer. That means the near ultraviolet to the SWIR 2 with a spatial resolution of 30 meters. What are the main differences between this instrument? First of all, the starting wavelengths of the EnMap, it's in 420 nanometer, and the EMIT in the near ultraviolet 380. This is the first satellite, Earth observation satellite, that includes this range. Okay, and the second difference is the spatial resolution, 30 meters versus 60 meters. So one of the obvious or the nearest study area is the Negev desert and Sinai. This is the political border. And if you look very carefully, you'll see the dunes, crossing the borderline, and there is no difference between the pedology, the geomorphology, the climate, the geology, everything is the same, but we see that the dunes on the Negev side are much darker than in Sinai. And to make a long story short, this is because the conservation policy of the government of Israel, which allow the area to be covered by biogenic crust, while there is a lot of anthropogenic activity in the Egyptian side, and all the crust are trumped by the herds and by vehicles and anthropogenic activity. So this is the main reason for the dark side of in Israel and the bright side of Sinai. Now, in order to distinguish between these two parts of the border, we are using, first of all, the brightness index, and this is a winter image of February 24. This is the equation of the brightness index, and you see, definitely you see that there is a lot of values, high values, or actually low values in the Negev and high values in Sinai. That means that Sinai it's much brighter than the Negev. Okay, the next is the Crust index. Crust index, it's actually derived by the pigments of the phycobilin. Phycobilin, it's a pigment that, if you remember from the previous slide, has an absorption in the blue. So we see a higher reflectance of the biogenic crust in the blue, and in the red and near infrared, the biogenic crust reflectance is lower. So this phenomena is enabled to create a, let's start from this. We extract the phycobilin and we see the signal of the reflectance of the phycobilin in the blue, and we derive the Crust index, which is a normalized difference between the red and the blue. And these are the image, the EnMap image of the same time with the Crust index, and obviously we see that we are getting higher values in the Negev than in Sinai. It's quite obvious. Okay, now again we are using a winter image, and we know that the microorganism of the biogenic crust is like plants. They turn green while they are wet, and you see here images of the January. I think these are the dates. All of them are winter images. You see that the area, the surface is green, while the perennials are still dry. That means that all the reflectance of the vegetation coming from the biocrust and not from the perennials. And of course, we can use the near-infrared NDVI index in order to distinguish between area with biocrust and without biocrust. The NDVI, just to remind you, is the normal difference between the near-infrared and the red. So this is the image, the derived image of the NDVI. As before, you see the difference between the two sides of the border. Okay, now we will go in order to not a pigment, but another element that exists in biocrust. These are the cellulose. Cellulose, it's one of the elements that build the cell, and what we see here, this is a image that I take from another paper. You see the spectra of wet lichens and dry lichens. And what we see that if we are looking on sphere 1 at 1.6 micrometer, the peak of the wet and the dry doesn't change, it exists. Okay? When we are looking on a sphere 2, we see that when the dry lichens, in the dry lichens, we see this trough, which doesn't exist when we are looking on the wet lichens. That means that we have here a special feature that we can use for distinguish between the or to map the dry lichens, and the index that we use here, it's a normalized difference between the sphere 1 and the sphere 2. And this again, the image of the EnMap showing the difference between the two sides of the board. Okay, so let's take the three pigments and the brightness index and the sky, the cellulose index, and we see that it's give more or less the same image, and this is the correlation matrix between the four, and we have a very high correlation between the sky, which is the cellulose index, and the NDVI 0.91, but all the other correlation are the same. Of course, the brightness index correlated negatively with the other indices. Okay, so until now, I present the EnMap, and I mentioned before that the EMIT has a very unique feature. This is the near ultraviolet values, spectra between around the 380 nanometer. And in this area, there is another pigment, it's called schistonemine, which this is the first time that we are using it for mapping biocrust. So the absorption of this is in the 380 nanometer, and we use this is absorption versus the wavelengths, and we are using the green area as a reference. So the 3 index is the green minus near ultraviolet, normalized by the summation of these two. And we are using the EMIT to map this pigment, and we are getting this image. Now we don't have the area of cyanide, but we can look about the difference between the northern part of the study area versus the southern part. I'm not going into the details what exists, which biocrust exists in the north and in the south, but you definitely see the difference. So I add all the other images that the other indices that I show you before, just to make this presentation shorter, and to see the correlation matrix also with a very, very high values between all the elements. let's concentrate just for one slide about the NDVI, because this is a very nice example. There is a gradient between the north and the south, as you well know, in the precipitation, but on this date, the 1st of February 2025, we see that this area has getting NDVI much higher than the surrounding. So we wonder why we don't see the gradient from the north to the south, and we found that there was a very heavy rain event in Sinai that also penetrate into the Negev, and there was during the previous 2 months there was about 65 millimeter of rain, and this is the influence of the or the signal of the NDVI after these rainy days. So I show you the results for the Negev. Let's go for other parts of the world. We were 2 sites in Spain, 1 site in Colorado, 1 site in Namibia, 1 site in South Africa, and the last one in Kenya. And what we see here, that we got the same features of the VIP in all the sites. You see here in Namibia, in Colorado, in Spain 1, Spain 2, South Africa, and Kenya. Just all these areas are located, all the important bands are located in the same region. So what are the take-home messages? The first one is that all the presented class indices are based on the solid physical and biological pillars associated with specific spectral bands, enable the biocrust mapping by hyperspectral Earth observation satellites. The second one is that the hyperspectral features of pigments and cellulose enable to refine the involved spectral bands on the satellite level. And the third, the same dominant spectral features were found in many desert wildfire. So thank you very much for your attention. Now questions.
And I have a question. Did you check the difference in the aridity in your study sites? Were they similar or were they different? Arid. Okay, and yeah, and another following question. You've done a lot of research on the dunes and the area in Egypt and between Israel and Sinai. Is that in any way similar to the other study sites, or are they very different in the dune? No, mostly in the geological patterns of dunes and sand. Or sand. Dunes. It's just interesting to see the difference in different soils, different aridity, and what we talked earlier was in different hyper-arid where biocrusts barely survive, if there's a difference in the spectral region there. Okay. I see what you mean. Okay.
With continuation for your presentation yesterday, I looked and I found also in a 20-30 nanometer also features. You see here? So probably your work also holds. It doesn't exist in the Negev. Okay. The Negev. Not sure that I show it here. No, it's in the one of the earlier. In the Negev it doesn't exist, but in other area you can find the 20-30 nanometer as one of the VIP features. Okay. Maybe. We have to investigate it. I didn't do it because it fits my goals. But, okay.
Buildings take a piece, and I think maybe
Are you sure that it's cyanobacteria, it's not lichens? Yeah, yeah. There is a walls and geological features of buildings and so on. Yeah. Yeah, yeah. We know that archaeological sites are covered by biocrust, and there is a big question if we want to clean it, because when you are cleaning the biocrust, you are destroying other features, other sites, or limit. One of the early papers that I read, it's the detection of biocrust on graveyards in Europe that exist 100 years. Okay, any more questions? So thank you very much for staying with us this afternoon, and I hope you enjoy from the lectures and enjoy also the rest of the conference.